My name is Professor Sarah King, and I am an assistant professor in the chemistry department, the James Franck Institute, and the Institute of Neuroscience at the University of Chicago.
Arnold Beckman was an entrepreneur and scientist, and he revolutionized all kinds of things that we use in science every day. The pH meter, which is ubiquitous in every laboratory pretty much worldwide, to the UV-Vis spectrophotometer, which really revolutionized how we could do medical diagnostics and just basic laboratory tasks. Arnold Beckman's achievements have had a large impact on my scientific career because I'm a chemist. This sort of discovery ethos of his, and the idea that if you take a better measurement, you can understand something that nobody else could understand before, is definitely something that I use every day in my lab. I have always been interested in what I would say like the broken places in materials. So I am interested in when the material isn't perfectly flat, or if it isn't all exactly the same. I'm really interested in how these types of variations and heterogeneity in a material change the material or the chemical's properties. The world around us isn't homogeneous. The world around us is complex and different and has all these kinds of variation.
One of the quintessential places where heterogeneity interfaces in materials is absolutely critical are things like the transistor or the batteries in your electric cars. And one of the things that we've been able to do in my lab is develop a new spectroscopic technique that allows us to probe electronic structure of interfaces. So what's an example of an interface? Let's imagine that we have water in an Erlenmeyer flask. And let's take a look at those water molecules in that flask. They might look something like this, where you've got all these different water molecules interacting with each other. But that's of course not the whole story. You also have water molecules that are interacting with the air interface. And those water molecules could look very different than the ones that we were looking at farther down in the Erlenmeyer flask. So how do we look at those water molecules? Well, we use a property called centrosymmetry, and the fact that the water molecules in the Erlenmeyer flask in the bulk have a chi2 which is equal to 0, meaning that they're centrosymmetric. Whereas the water molecules at the air-water interface have a chi2 that's not equal to 0, meaning they're non-centrosymmetric. And that matters because the interaction of light with materials that have a chi2 not equal to 0 is very different than the interaction with light with materials that have a chi2 equal to 0. And you can use that difference in order to be able to selectively investigate, for example, the water molecules at that air-water interface. But what about situations where it's not just water? What if we're making salad dressing and we have not only air, but we have oil and water? What happens in that type of a situation? Well, then you have multiple interfaces that you have to consider, and that then becomes really complicated in order to be able to probe them selectively. Now, of course, this situation is not unique to, for example, making salad dressing. It's also present in things like, for example, electrodes of a photovoltaic cell. Photovoltaic cell is made up of two electrodes with a photoactive material in between. When they're hit by light, or a photon, with an energy h nu, this then can create an electron-hole pair in the material. Because those two photoactive materials, A and B, for example, have slightly different properties, that can result in a separation of your electron and hole pair at that interface between these two materials. And then what happens in order to make this work as a photovoltaic is that those electron and hole go to different electrodes. And all of that is predicated upon the interface and its electronic structure. In order to probe that electronic structure better, we've developed a new spectrometer. And this spectrometer design allows us to directly track the phase relationship between two waves, shown here by the delta phi.
What we're doing is an interference measurement where two pulses have to interfere with each other. We're using the phase difference between them. If our phase is unstable, we don't get accurate spectra at the end of it.
Thanks to the flexibility and support of the Arnold and Mabel Beckman Foundation, we've also expanded our investigations of interfaces to in situ spectroelectrochemical cells in order to probe the electron transfer dynamics at realistic and working electrochemistry situations and interfaces. In the future, we hope this will help us design better interfaces for water splitting and conversion of carbon dioxide to value-added fuels.
The Beckman Young Investigator Award has been absolutely crucial for launching my research group and my career in science. I think one of the things that's been most important is just the flexibility that it's given me and the ability to try risky things. And I think that kind of investment over time compounds.
The Arnold and Mabel Beckman Foundation have my sincere thanks for their support, and I look forward to our future discoveries.